Good morning, everybody. Thank you for coming. And today we will have a very nice talk by Dr. Humberto Campins from the University of Central Florida in Ontario, United States. And he will talk about these planetary defense solutions. Dr. Humberto Campins studies asteroids, especially those that can be threatened Earth with an impact. He's a Pegasus professor of physics and astronomy and head of the planetary science group at the University of Central Florida in Orlando. In 2010, he led the team that discovered water ice and organic molecules on asteroid 24 Themis. This was published in the journal Nature, adding weight to the idea that some of the Earth water come from asteroids. He was a 2021-2022 Jefferson Science Fellow and served as a science advisor at the U.S. State Department Bureau of Education and Cultural Affairs. He's a member of the NASA OSIRIS-REx asteroid sample return mission, which is on its way back to Earth and arriving in September of 2023. He also works on European Space Agency projects, including the Euclid, Gaia, and Hera missions. So thank you, Humberto, for being here. And I give you the floor with the talk.
Thank you, René. It's a pleasure to be back in Granada. My first visit to the IAA was in 1993. That was actually my father who did that. No. And I gave a talk about the likely impact of a comet that had just been discovered with Jupiter a year later, in 1994. Most people in the audience didn't believe me, but Fernando did. And we ended up observing it a year later from the William Herschel telescope in the Canaries. It was fun. Anyway, so I'm delighted to be here. And so I'll be telling you a little bit about planetary. Can you play Pac-Man here? Yes. Oh, okay. So I should use this one? No. Okay. Okay. So there we go. So here's a quick outline of what I'll be telling you about. A quick introduction to asteroid impact hazards, then these two current collaborations on planetary defense for international collaboration for planetary defense, OSIRIS-REx and Hayabusa 2, and then NASA DART, that there are members of the mission here, including Fernando, and then LICIACube and the Hera mission. And then I'll tell you a little bit about my work on OSIRIS-REx, which is still ongoing. And it's the fact that we found rocks on Bennu that formed on another asteroid. And this is a very interesting discovery. Okay, so how likely is an asteroid to ruin your day? Not very, as most of you probably know. The chances of that happening while we are alive are so low that as individuals, we don't have to worry about it. We can worry about other things, but this should not make us lose any sleep. As a civilization, though, we must do something because big impacts have happened and big impacts will happen again unless we do something about it. The dinosaurs did not have a planetary defense office. And they're not with us anymore. So the Planetary Defense Office at NASA includes considerable international collaboration for planetary defense. There's a number of projects, including the DART mission, which was funded by this office. And it was featured in the recent movie, Don't Look Up. Just for my curiosity, how many of you saw Don't Look Up? Okay, so you guys know what I'm talking about. Now, in reality, my colleagues there are much cooler than in the movie. They would not bring a professor from Michigan State and his graduate student, no matter if she's Jennifer Lawrence, they would not bring them to the White House. They would filter that information and pass it on up. But the movie was good. I thought it was compelling. Anyway, so OSIRIS-REx and Hayabusa 2 and the DART, LICIACube and Hera are these collaborations that are partly funded by all of these space agencies that are trying to defend our planet against an impact. OSIRIS-REx is the one I'm a member of, and I'll tell you most about this mission. Hayabusa 2 successfully went to asteroid Ryugu, picked up 2 different samples, and brought them back to Earth, and they're being analyzed, and I'll be telling you a little bit about some of the results. And then OSIRIS-REx picked up 1 sample in October of 2020, and will be returning it back to Earth to the Utah desert in September of this year. Okay, so Bennu and Ryugu, a tale of 2 asteroids. Both are potentially hazardous asteroids. So right now we do not know of any asteroid that can cause global devastation that is threatening Earth. So that's nice to know. It's good. We can relax on that front. But there are potentially hazardous asteroids that have orbits that could evolve into one that can threaten Earth in the future. So both Bennu and Ryugu are those. And so they're not an immediate threat, but we have to worry about it. They have similar orbits. OSIRIS-REx went to Bennu, Hayabusa 2 went to Ryugu, and here's the orbit of Bennu. Comes in within the orbit of the Earth slightly. It goes about 3/4 of the way to the orbit of Mars, and it has a very low inclination, so it's easy for us to send spacecraft there, and it's also relatively easy for its orbit to evolve into one that would intersect Earth. Same with Ryugu. The orbit of Ryugu comes slightly within the orbit of the Earth, and it goes essentially all the way out to the orbit of Mars. And I was giving this talk a few months ago, and somebody from the audience said, could we use Ryugu as a way of transporting material from the Earth to Mars? And I hadn't thought about that until that question. And I thought about it for a little while. And it turns out, yes, you can, but you cannot be in a hurry. The lining up of the orbit of Ryugu with the Earth, and then the lining up of the orbit of Ryugu with Mars, it doesn't help to have Ryugu be here and Mars here, right? It has to line up with Mars. So that can take, I don't know, 10 years or so. So if you take a lot of supplies for the Martians, for the people that are colonizing Mars, you put them on Ryugu, it's going to take about 10 years to get there, but it's a lot cheaper. So you might just put low priority material and do that. Anyway, this is Bennu. These are December of 2018 images that we took when we first got there, and we were a little bit surprised at how rocky it was, and its rotation that we didn't know about every 4.3 hours. This is Ryugu, and about 6 months earlier, obtained with the Hayabusa 2. The 2 of them look similar, but they're different sizes. And hold on a second. Well, I'll discuss the 2 sizes and the predictions in a second. So because I am on OSIRIS-REx, I'll tell you a little bit more about it. Our 4 main themes for OSIRIS-REx were revealing solar system history, so bringing back a sample of a very primitive asteroid to study the organic material and the other components of that object, to try to understand how the solar system formed and evolved. And most importantly, for our proposal to NASA, the main scientific question that OSIRIS-REx was going to pursue was the organic material on these asteroids and what that would tell us about the prebiotic organic material on Earth. I'll discuss that more in a bit. Another one would be mitigating impact hazards. I've already told you a little bit about that. So like Bennu and Ryugu, if they're going to threaten the Earth in the case of Bennu in another 140 years, and we need to deflect it, we need to know as much as possible about it so that our deflection technique works. Enabling human exploration. Humans want to get to Mars. Chances are that we're going to have to stop in the moons of Mars, Phobos and Deimos, which are captured asteroids. So by doing activities on Bennu and Ryugu, we are enabling future human exploration of the moons of Mars, and of the mission to the surface of Mars. Chances are we would send robots to the moons of Mars to process the material and obtain fuel for us to go from the moons of Mars down to the surface of Mars, where we would likely process material there and generate fuel to come back. So we would make several stops, just like Columbus didn't go all the way from mainland Spain to the New World. He stopped in the Canary Islands and got some supplies, right? So we're likely to do that. And then developing a space economy. This is, I think it's particularly interesting because asteroids are ideal resources for developing a space economy. Soon, I don't know how soon, but a decade, no more than two, it will be cheaper to process an asteroid and obtain water than it will be to launch it. The moment that you get fuel from an asteroid cheaper than it costs to launch it into space, you're going to have all of these customers that want to buy it, because they're all the Earth's orbiting satellites are going to want to prefer to buy the fuel cheaper in space than to put it into orbit, which will be more expensive. So that will get a very vigorous space economy where the people mining the asteroids will be paid by the people who want to buy the fuel from Earth orbiting satellites. In addition to that, communication and other satellites, for example, for gathering solar energy, can be 3D printed in space with asteroid materials. So we would be printing structures in space that don't have to even withstand the gravity here on the surface of the Earth. They're going to be operating in a very different environment where they would never have to be put into a small cylinder, shaken up, subject to several G's as it goes up into space. So, for example, imagine if the 3D printing of most of the Webb Space Telescope in space and only launching the material that was essential to build on Earth and incorporating that into the telescope, instead of building a very complex object telescope that has to fold onto itself, be put into a tube, launched, and then unfold into space. And the reason why it took a lot longer and was a lot more expensive was because they needed to make sure that it worked perfectly, because if it didn't, like the Hubble Space Telescope, there was no chance of repairing it. So I think that this is going to open up all kinds of interesting space structures or Earth orbiting structures that never have to be built on the surface of the Earth. Okay, so this is something that I was surprised, and I guess it showed how naive I was. When I was invited onto the OSIRIS-REx team before we got our proposal granted by NASA, I realized that we were going to be only the fourth NASA mission to bring back extraterrestrial material. First one was Apollo, lunar samples. Then it was Genesis, the solar wind. Stardust brought back dust from the tail of a comet. And then OSIRIS-REx is only the fourth NASA mission to bring back extraterrestrial materials. So this is exciting, and I was very honored to be part of that team, and even more excited to be funded by NASA to do this. And a little bit of a summary of all the asteroids that have been visited by spacecraft. And of all of those, the only two rendezvous missions, or the only three rendezvous missions, have been the ones to Eros, then Hayabusa 1 to Itokawa, Hayabusa 2 to Ryugu, and then OSIRIS-REx in September of this year. I'm sorry, and these are to near-Earth asteroids. There's been two rendezvous missions to Ceres and Vesta, which were done by the Dawn mission. Okay, so most of what we predicted about Bennu and Ryugu matched quite well. The global properties, the spin top shape, the composition. So we had made observations of Ryugu before encounter, mostly with radar, and we predicted its size and its rotation rate quite well. With Bennu, we had made even more observations. We had been better characterized before we got there, and turned out to be roughly what we intended, what we anticipated. So we were so comfortable. So we were so smart. We predicted all of this, and this is what we found. We are smart. Ha! Until we expected areas of coarse sand or pebbles on the surface. Essentially, the beach, half an hour from here, no big rocks, nice sandy beach, right? This is what we found. Okay, so that rock is about 3 meters tall, and there's no sand there. There are really sharp rocks everywhere on Bennu, and so no loose sand or pebbles. So the spacecraft was already there, and we were planning on going down to the surface with an altimeter, with a laser altimeter, and expecting a nice smooth area without rocks. And then we would just come down, no danger, and then come pick up the sample and come back up. We had to change that whole approach. So the navigation team, and my hat is off to the navigation team of OSIRIS-REx, they had to rethink how they would do this. And they uploaded a program that made the spacecraft completely autonomous. So it would fly over the area that was going to be sampled, and it was going to use that map as a reference point. And as if it came down to do the sampling, which had 2 rehearsals before we actually did the sample. But as it came down to do the sampling, it was going to be correcting its trajectory constantly, so that if it was getting too close to this rock or to that rock, it would make corrections and sample the center of the crater, which was called Nightingale. All this had to be done when the spacecraft was already at Bennu. So they did a great job with that, and this is the artist's conception of our sampling maneuver before we got there, right? So the artist expected a smooth asteroid without big rocks, no problem. And we're going to come down, sample, and move away. Well, it turned out to be much more complicated than that. But this, I also use this to illustrate the fact that we had to come down vertically with near zero velocity and horizontally with zero velocity, which was not necessarily trivial if you remember that this asteroid was rotating every 4.3 hours. So the spacecraft performed this maneuver twice before it actually sampled to make sure that all the bugs or all the kinks were worked out, and then we successfully came down to the surface and sampled. What you'll see here is a series of images of the sample maneuver. When the head of the mechanical arm, the sample mechanism, which we call the TAXAM, touches the surface, it fires nitrogen to fluidize the dust and make it go into the container. And it there have been a couple of papers already published on this, but what we encountered was material that essentially offered no pressure at all, no force on our mechanical arm. And had we not fired the thrusters to move away from Bennu, the whole spacecraft would have been buried inside of Bennu. There was no friction, no cohesion. It was remarkable. In any case, we collected so much sample that the seals on our container didn't quite close. And so when we took images of the sample head, we could see particles just drifting away. And I was at a meeting where we were discussing this, and the head of the mission said, "There goes somebody's PhD thesis." Right? And so instead of extending the mechanical arm and rotating the spacecraft to measure the mass that we had, because we had done that before we obtained the sample, so we're going to do it again and measure the difference, and that was going to give us the mass of our sample. We decided to just put that sample into the capsule, seal it, and head back to Earth so that we wouldn't lose any more mass. So that's what we did, and then we did a little bit more of a reconnaissance of the sample site, but the sample was safely in our capsule. Hayabusa 2 had already gone to Ryugu, sampled once, and they were not satisfied with that. They decided to shoot a projectile, create a fresh crater, and then sample the crater, and then head back to Earth. If I had been the head of that mission with the training that I got from NASA, I would have headed back when I had the first sample. I wouldn't have risked the spacecraft with a sample already in it, doing this very interesting maneuver. But my hat's off also to the Japanese. They have guts. They are much more tolerant of risk than NASA is. And so they did this, and it was remarkable. One thing that was funny is that in order to hit the asteroid with a projectile, is they left a small cube-sized type thing that shot the projectile onto the surface. In the meantime, the spacecraft, in order not to be hit with the debris, went and hid behind the asteroid, so that the spacecraft would be safe while the projectile hit the asteroid. Which reminded me of me when I was a child, and I would, light a firework and then go hide, and then let's go see the crater that left over. So the Japanese took me back to my childhood. In any case, the good thing is they already got their sample. They already gave us 10% of their sample, which is half a gram. So they brought back 5 grams. So they already gave us 10% of their sample, which is being analyzed in American laboratories. And they have some interesting results. And when we get our sample back, we're going to give them 10% of our sample. So we're going to be sampling at least 2 asteroids for the price of 1, thanks to international collaboration. Okay, so I'm going to now talk briefly about this, although I think most of the audience here knows a lot more about this, because even though part of this is an American mission, DART, LICIACube and ESA's Hera are European. Okay, so DART hit Dimorphos in September of last year. And then just about 10 days before the impact, LICIACube separated from DART. It was attached to it, separated, took some images of the impact, and they made Dimorphos change its orbit. So it was a huge success. And Fernando can tell us a lot more about that. He actually calculated how much mass was ejected and all the interesting things about how it was ejected. So this is fascinating. And it turns out that the behavior of this asteroid and the behavior of Bennu are somewhat related, and we can learn from each other on that. So it's all very positive in terms of using this technique to deflect an asteroid like Bennu if it's threatening Earth in the future. And there were many Earth-based observations, including this was from DART a few seconds before impact. This is the last image before impact. This is an image from the Hubble Space Telescope, and it's a complex eject, and it tells you a lot about how the material was ejected, the sizes, all these things, the energy, the mass. Hera is being built and will be launched in 2024, so next year, and get there in 2026 to study the crater from DART and other characteristics of Dimorphos and of Didymos in detail. So again, the more we learn about the results of this impact, the better we'll be able to deflect asteroids in the future. Okay, so Hera is going to do a crime scene investigation. I took that from the Hera website. Launches in October, and then it rendezvous with the asteroid in December of 2026. Okay, so the conclusions from section 1 and 2, and then I'll go on to a little bit of my work. Planetary defense against asteroid impacts benefits extensively from international collaboration. OSIRIS-REx and Hayabusa 2 brought back the samples, or Hayabusa 2 brought back the samples with OSIRIS-REx will this year. And then we got more and more interesting missions that are testing this technique of a kinetic impactor against an impact of an asteroid. Okay, so let me tell you a little bit about some of my work on OSIRIS-REx. In 2009, I was here in Granada at a planetary defense conference, and there I learned about 2008 TC3, which was the first asteroid that got discovered outside of the atmosphere, entered the atmosphere, and then was picked up as a meteorite in Sudan. And I was interested in that and read about it and continued to follow those things. And it turns out that most asteroid dynamicists, or most solar system dynamicists, tell us that in an asteroid impact, the projectile is likely to be vaporized because the average speed between asteroid in impacts is about 5 kilometers per second. And so nobody expected anything on the surface of an asteroid from a catastrophic disruption. And it turns out that I had been telling the team for about 2 years about this, and most of the team didn't believe me. I was joking that they almost sent me to Guantanamo to be waterboarded because I was telling heresies. Projectile surviving impact, impossible. But what motivated me to link TC3 with Bennu is that when I studied the orbits, because I did an analysis of the orbit of Bennu and where in the asteroid belt it's likely to come from, it was from the same area where TC3 came from. So I thought, maybe the two of them aren't related, and we could have, in the case of Amahatasita, the meteorite, it was the most unusual meteorite we have ever seen, still, till this day. Instead of having one type of asteroid in there, it had 5 types represented. The Uralites, the 2 types of ordinary chondrites, instantite chondrites, ordinary chondrites, and I think that since I've been following the literature on Amahatasita, maybe more class have been discovered. So 5 different asteroids had to form, break up, come back together in a non-erosional process to produce Amahatasita. When I saw that TC3, which produced Amahatasita, came from where Bennu came from, I predicted to the team that we should have bright and dark pieces of the surface of Bennu. And several people took me seriously. Most people didn't believe me. Danny Della Justina, the head of the imaging team, the 2 people that built and headed the spectrograph, and Marco Delbo from Nice, which had worked on similar problems in the past. So one day, Danny Della Justina invites me onto her office in Tucson, and she says, Humberto, look, didn't you predict bright objects on the surface of Bennu? I said, yeah. She goes, I've discovered at least 6 boulders that are much higher albedo. And so the reflectivity of these, albedo is the solar system term for reflectivity. So these 6 boulders had between 13 sigma and 40 sigma above the median reflectivity of the surface of Bennu. I'll show you a little graph of that. And then she said, not only are these things much brighter than the rest of the surface, their colors are strange. They have a drop at the longest wavelength, which could be consistent with being some kind of a silicate. And then we got the spectra of these boulders, and I'll show you. They indicate a very particular type of silicate, which is what essentially lava is. So this is pyroxene, which is what we would find on the surface of Vesta. And it was so distinctive because Vesta is a unique asteroid in the asteroid belt. And it's the only, well, I won't go into too many details, but its spectrum is very distinctive. Vesta and the Vesta family are the only ones that have that spectrum. So we identified things that were much brighter and looked like Vesta. Then after, and I'll tell you some more about that. Then we did a more detailed study of Bennu, and we found 71 other boulders with the technique of looking only in the camera colors. We identified these first 6 that had already been identified by Della Justina et al. We identified 71 others. And then Eri Tatsumi had done a study on asteroid Ryugu, and they found a number of objects on the surface of Ryugu that were also likely came from elsewhere, but their composition was more typical of S-type asteroids, which are linked with ordinary chondrites. So this is interesting because both asteroids had material that came from other asteroids. So this thing about Amahatasita being unique and completely unusual is not holding up much. But it's also interesting that Bennu has at least six rocks that look like Vesta. And Ryugu has many rocks, but they look more like ordinary chondrites, like S-type asteroids, which is not Vesta. So these are the 6 rocks in were published in the Della Justina et al. Paper that we published in Nature Astronomy. And you can see that their reflectivity is much greater than their surroundings. And their spectra, oh, I'm sorry, and here's the average albedo of Bennu. It's peaked at 4.5%, and it's a very sharp peak, and between about 3% and 6% reflectivity. That's the rest of the surface of Bennu. And our rocks were outliers. They had an albedo ranging as high as 21%, so way over there, right? So statistically, they belong to a very different population based only on the reflectivity. This is where we found our first 6 rocks. This is the surface of Bennu, and these are the spectra. So these are the 6 rocks that we identified initially, and these are the spectra, except for this one that doesn't have a strong 0.9 micron absorption. All of them have this 0.9 micron absorption, which was what Danny Della Justina was telling me when she first pointed them out. So when we got the spectra, we got 0.9 and 2 micron absorption. And when you analyze these spectra, they're clearly a pyroxene, and not just a pyroxene, but the type of pyroxene that you see on the surface of Vesta. So we linked pieces of Vesta, and here's an image of Vesta taken by the Dawn mission on the surface of Bennu. So these are the other potentially exogenous material that we identified on Bennu based only on the camera. So we have spectra for these 6. These other ones, we have only the 4 colors of the camera, but based on those 4 colors and on the reflectivity, we identified them as likely to be exogenous also. Now, formation scenarios. So the average collision speed in the asteroid belt is 5 kilometers per second, which is too fast for fragments to survive. But they do. That's not a problem for me. I'm just an observational astronomer. I just report what I see, right? Now, the theorists are having a problem. And some of my best friends are theorists. So we're missing something. So on Bennu, on Ryugu, and on meteorites like Alma-Hattasita, whichever process it is, when they impact each other, they don't vaporize. They don't. The impactor doesn't disappear. So we're missing something. The fact that Bennu has pieces of Vesta on it is very interesting. And the fact that Ryugu doesn't seem to have pieces of Vesta on it is also very interesting. This can help us understand the collisional evolution of asteroids and the processes that form Earth and the other terrestrial planets, because they form in a way similar to the way that asteroids form. And it's also interesting that the samples from OSIRIS-REx could contain pieces of Vesta. I hope so. We don't know. We will find out once we have those samples in the lab. But we may have samples from Bennu, samples from Ryugu because of the international collaboration, and we may even have samples from Vesta on Bennu, and maybe samples from other asteroids on Ryugu. So this is better than we had anticipated. Now, what makes pieces of asteroid Vesta on Bennu so interesting? Well, Vesta is got a unique volcanic composition, which is very easy to identify. But why Vesta and not more abundant S-type asteroids fragments on Ryugu? If you look at the inner asteroid belt, the pieces of Flora, the Flora family, which is an S-type family, are much more abundant than the pieces of Vesta. Could it be that was the timing of the impact? So Vesta forms, it has 2 large impacts that create 2 large craters, which are Venenea and Brasilia. So could it be the timing of those that happened before the formation of the Flora family? We don't know, but we're looking into that. So because we know the ages of Venenea and Brasilia on Vesta, and we know the age of Flora, we may be able to constrain the timing of when Bennu was formed, which is interesting and may be, we may be able to understand the collisional evolution of those families and of the inner belt a lot better than we have anticipated. So, and these Vesta fragments may have been the ones that impacted the parent body of Bennu and produced Bennu. But again, theory tells us that the projectile doesn't survive. So why? We don't know. So, in conclusion from the last part is that Bennu has at least 77 boulders on the surface that are believed to be from another asteroid or other asteroids, plural. And it's at least 6 of Bennu's boulders are from Vesta. They're much brighter. They have a pyroxene spectrum, which ties them directly to Vesta. And in the case of Ryugu, there are these bright rocks that have about the same size distribution of those that we found on Bennu, but are more consistent with a different type of asteroid. So it could be that the Ryugu samples contain some fragments that are from S-type asteroids. So in which case we would have sampled, if we're lucky, and Ryugu has pieces of S-type asteroid, and Bennu has pieces of Vesta, we would have sampled 4 asteroids with 2 missions. Anyway. Okay, so this is what my presentation was going to be until now. Dr. Dufard asked me if I would comment on the paper in Nature about the detection of one of the bases of the RNA molecule that was found on the Ryugu sample. So the sample from Ryugu is already being studied. This is one of the results. And so organic molecules in asteroids also, first of all, organic molecules on the Earth are likely to have come from asteroids and comets. That's because when the Earth formed, it had a stage which was called the magma oceans, where if there was any organic material, it would have burnt. So Earth and the Moon both went through this phase where the surface was molten rock, and if there were any organics, they burnt. Slowly, that rock cools and solidifies, and you get a solid surface. Impacts with comets and asteroids bring the Earth its organic molecules. And so in meteorites, these organics, most meteorites come from asteroids. But the difference is that in meteorites, the organics are subject to terrestrial contamination. So they only study the insoluble ones because they are reliably extraterrestrial. When you get a meteorite, it's very difficult to determine if any organics in there are a terrestrial contamination or are original from the meteorite. So they basically don't even try. However, on the Ryugu samples, which are truly well curated and don't have any terrestrial contamination, uracil has been detected, and it's one of the 4 bases for RNA, but not for DNA. And this is interesting. So I'm just reporting on what was published in Nature. This is particularly interesting because the people who think about the origin of life on Earth think that there was a stage of living beings that was previous to the current ones that use DNA for their genetic code, and it was based on RNA. So if they have discovered one of the bases of RNA, it may be giving us clues about how organic molecules created the first living cell on the Earth based on the inventory of organic molecules on asteroids as opposed to on Earth, because on Earth, all the organic molecules have now been transformed by Earth, and any record of what the prebiotic organic inventory has been erased by life itself. So RNA has been suggested as a stage of life on Earth before the current DNA-based one. And so the uracil detected is an example of exactly what Hayabusa 2 and OSIRIS-REx were designed to accomplish, which is the practical question of both of these missions was, these are potentially hazardous asteroids. Let's study them to see if we have to deflect it. The scientific question for both missions was, let's study the inventory of organic molecules to see what existed on Earth before life formed and try to understand how life formed. So this is this result is exactly what we were hoping for, and hopefully there's going to be a lot more. Questions, discussions.
Thank you, Humberto. So,
and is somebody checking the questions online?
yeah,
Okay.
yeah.
Thank you.
First, we take question here and then
Online. Okay.
So, question here. Yeah.
Well, thank you very much for this talk being fantastic. I do nothing like this, and you got my attention all the minutes. So going great. One of the things that got my attention though is that you mentioned, I think, casually that maybe one of these asteroids will hit the Earth in 140 years.
Yeah,
I mean,
Bennu.
you studied that very casually, but this is tomorrow. I mean, it's very
and this is again our two main justifications for OSIRIS-REx to NASA. I mean, it's like, NASA, give us $650 million. Why? Oh, because this asteroid is potentially hazardous, and we got these scientific questions to address. And they did. I mean, we had to beat 13 other proposals, but yes. So Bennu and Ryugu are potentially hazardous. We could discover others that are potentially hazardous, or we could discover others that are hazardous. But these are the ones that have the highest chance of having their orbits evolve into something that is going to threaten Earth. So the chances of Bennu impacting Earth in 140 years are still very low, or actually they're essentially zero now. But we suspect that the evolution of the orbit could make it a hazardous asteroid in about 140 years. And so if we need to deflect it, we want to be ready. And one of the ways at which we're getting ready is missions like DART that are testing this kinetic impactor. There are other techniques, but this is something that we need to work on constantly, because the longer we detect an asteroid before impact, the easier it is to deflect it. And we don't know which asteroids are threats. I mean, right now, none of them is an immediate threat, but we don't know what could be discovered, especially among the smaller ones, which could be discovered shorter times before impact. So this is a whole area of research in the US, funded by the Planetary Defense Office. And they actually have, there's a European and there's an American mission, both of which would be going inside of the Earth's orbit and looking out at things that we miss, because from Earth, those things would be near the sun. And so these guys are looking out there. They detect these things easier, and they can go smaller, and they can study things that could be, let's say, 140 meters in size or greater, that could threaten a city. Not global devastation, but if they're threatening a city, we should try to do something about it.
And if this asteroid were to impact the Earth, what would be the damage? Like
Bennu would cause global devastation. The amount of dust that would be kicked up into the atmosphere would produce a winter that would last several years. All the crops would fail, and civilization would collapse, because if there's no food, you can imagine what's going to happen, right? It would be even worse than if there's no internet. Yes.
Are there any chances that the boulders that you found on Bennu are from another asteroid with a similar formation to Vesta, that now it doesn't exist anymore, for example? Very naive question.
It's possible. The thing is, the inner belt has been fairly well characterized as the innermost part of the asteroid belt. And we know that in the inner belt, there is the Vesta family, which comes from these two impacts on Vesta. It's well understood, and you tell me, you're more of an expert on that, but it's possible. But given that the pieces of Vesta are still there and they overlap in orbital space, the Polana family, which we think is the most likely origin of Bennu, that was an article that I wrote in 2010 saying Bennu is likely to come from the Polana family. And then I was looking at Amahatasita and TC3, and when I looked at the fact that the two orbits were so similar, then that's what led me to predict this. But there's nothing else in the inner belt like Vesta. Actually, there's nothing else in the asteroid belt like Vesta. There is an asteroid similar to Vesta further out, Magnia, but its composition is different.
Yeah.
So it spectrally it would look slightly different. So the answer is yes, but the most plausible answer is Vesta.
Or another asteroid that disappeared.
Or another asteroid that no longer exists and happen to have the exact same composition as Vesta. This is why it would be, yeah. Yeah, and this is why it would be really fortunate, and I knock on wood, I hope so, that we have a piece of Vesta in the sample that we're bringing back from Bennu. We're bringing back about 250 grams, so it's maybe there's one little grain in there that is Vesta. It would be easy to identify.
In fact, if you see the spectra looks like it's very different between them.
Yeah.
The second band center is very different between each other. That tells you a lot of
variety
and the composition is difference.
Yeah.
So it could be difference in the depth of the crater of Vesta or in other approach.
Yeah. No, but we did go through an exhaustive comparison with meteorites and we compared it with Magnia and all that. And we ruled out anything that was not an HED meteorite or the Vesta family.
Probability is coming from the inner layer, which is Vesta.
Right. But it would be interesting, for example, to do a more careful, remember, this is, oh, we discovered this, we better publish it, boom, right? And now that we have more time and that the sample is coming back to Earth and we no longer have all the obligations for the mission, to look at this and start comparing the spectrum more carefully with not just meteorites and Vesta, but different mixtures that we might say, oh, this one has more olivine, this one has it's pure pyroxene, or etc. So that's something that maybe we can collaborate on.
So you have some pieces of Vesta on OSIRIS-REx sample. You can do oxygen
Isotopes, yes.
to determine if it is
Yeah. Well, if we do,
yeah.
right?
More questions?
Right, thank you. I have two questions. The first one, I couldn't hear you. Oh, sorry. My first question is the piece of Vesta that you find on the asteroids. As they are located in one place on the asteroid, or are they homogeneously located on the asteroid?
That's a good question, and let me go back in my slide to answer it. Forgive me for going so quickly. So these in blue were the 6 original ones that we identified. And then in red were the other 71 objects that we identified. These were identified as a combination of reflectivity, colors, and spectrum, right? These other 71 are on reflectivity and colors. We didn't get spectra of them because the spectrograph didn't cover the entire asteroid. And so they're more or less evenly distributed, although there seems to be a paucity of them here. And we did not look anywhere below 70 degrees or above 70 degrees, simply because the projection effects would make our uncertainty so great. We can go back and try to do that and maybe identify more over here. We just haven't, right? But our first 2 papers were, 6 boulders that were exogenous, 71 more that are likely exogenous. And among these 71, we seem to have 2 different compositions, and just from their colors. So it could be that we have S-type material on Bennu, but we also have Vesta material. No question about it. In the case of Ryugu, they don't have any evidence of something like Vesta on them. So it could be that Ryugu formed after the Vesta material was no longer widespread, or it was hit by a piece of flora and not by Vesta. We need to look into that in detail. We haven't.
Have another question?
Yeah, but I see the response also is, do we know if we have some part of Bennu on Vesta?
Do we know a part of Bennu on Vesta? Ah, that's a good question. Not necessarily, because remember, if the parent of Bennu was sitting there in the Polana family, minding its own business, no problem, life is good, and whammo, it gets hit by a piece of Vesta, then Vesta itself would not necessarily be affected by that. But if the Polana family forms, or another C-type object forms, and impacts Vesta, then we would have dark material on the surface of Vesta. That was discovered by the Dawn mission. They discovered dark, hydrated material on the surface of an asteroid that's supposed to be completely volcanic. So the two of them are incompatible. So we do have pieces of C-type asteroids on the surface of Vesta, which is believed to be impacts that happened after the surface of Vesta had formed and was collisionally evolving with impacts of carbonaceous asteroids. Yeah, so that's a good question and a good point. We don't know if it's from Bennu, likely from another C-type asteroid that was closer, but yeah. You want to show the shall we show the yeah, given your question, let me show, how do I do it?
Rocks can move. Yeah.
Yes, the rocks can move. Actually, they do move. So this, what I'm going to show is the video that was produced by Julia de Leon, a colleague from the Institute of Astrophysics of the Canaries. I was on her PhD committee 14 years ago, and she defended her thesis, and she said, by the way, those of you that don't know, I have one more figure for the thesis. And she shows us this video, which was professionally produced, and nobody on the PhD committee knew about this. So it's the Earth, we go by the moon. She teamed up with a professional video production company that did this for free. But we're going out from the Earth, we encounter Mars, and now beyond Mars, we're entering the asteroid belt, right? And you start to see some of the asteroids and some of the dust produced by collisions between asteroids. And then they try to illustrate something called the Kirkwood gaps, which are areas in the asteroid belt that in orbital element space, there are no asteroids because of the influence from Jupiter and Saturn. And they illustrated in a 3D version here, which is not realistic, but anyway, the point they were trying to convey as much science in this video as possible. So in one of these gaps, they go in there and they accelerate time, and you'll see that the time is in años, so it was done in Spanish. And as these objects enter these Kirkwood gaps, their orbits are changed dramatically and they get ejected. And so all of this is interesting until you get to the climax of the video, which is coming up. Dramatic music. That could be an S-type asteroid, which is the most common in the inner belt. Uh-oh.
You think Ryugu is formed from one event?
Not necessarily, right? So Julia went to this company and they made this video for her for free. And none of us in the committee, at least I didn't know anything about this until she showed it. And since then, I've been showing it on almost every chance I get because of it. And what I do is that every time there's a PhD student that wants to get his or her doctorate with me, I show them the video and I said, if you don't get an Academy Award nomination, you don't get your PhD. and they still work with me, but you know, I do show it to them seriously. I said, this is not what I expect of you, but it's an example of what one of the students in the Canaries did, went way beyond what was expected and used this for basically for public outreach. But in any case, it illustrates how gravity will pull this material back and why Bennu Ryugu dimorphous are rubble piles. And so what she illustrated here was two big asteroids of about the same size colliding. That's not the most common event. Much more common is a small projectile hitting a large asteroid at a high speed. And because there are many more small objects than there are big objects, so the more common collision is going to be a small one with a big one, or a small one with a small one, but the catastrophic disruption ones will be a small one with a big one. So in the case of Bennu, there was at least one catastrophic disruption, maybe more than one. But the more you have, the less likely you would have for material to survive on the surface. I don't know.
Right. You are thinking in impacts and not in accretion.
Because you need to somehow break up the parent of Bennu.
You did it. Now
Okay.
you have the material. And then you start to accrete here and form different rubble piles.
So, okay, so that's a good point. So you're saying accretion instead of impacts.
So the
But
fragment survives.
But the average speed between asteroids, which has been, statistically characterized from all their orbits, the average speed between asteroids is 5 kilometers per second. Let's say that there's a Gaussian and you have some slower speed, but still, even the end of that tail is fast enough to vaporize almost anything. We're missing something.
It's not
Right?
old calculation, like for the bigger one.
Yeah, I think it's old, and I think the calculation doesn't take into account impacts onto rubble piles and tangential impacts. And so, yeah, but there's no question that large fragments survive, right? That's a fact, right? You have bright boulders on Bennu that have a very different spectrum from its surroundings. They're very different reflectivity, they're very different colors, and some of them are embedded into other rocks. Some of them seem to be individual rocks. It's even the morphology may be different from its surroundings. We haven't looked into that, but yeah. But does that answer your question? Yes.
I have another question. A few days ago, I received a message from a friend worried because apparently NASA identified new asteroid with impact in 2046. Is it true?
Yeah, and the chance, that is a valid detection. It will be back in 2046, and the chances of impacting Earth is something like 0.6%. And a relative of mine sent me a text message saying, and the headline was on Valentine's Day 2046, there is it's likely that an asteroid is going to impact Earth and ruin the day for lovers. Okay. Well, and further down in small print, 0.6% chance back then.
Don't worry, because they were friends.
Well, that's right. And since then, the asteroid's orbit has been refined, and the chance of impact continues to go down, right? And I told my relative, I said, if somebody told you that you're going into this business that has a 0.6% chance of succeeding, would you call that likely? No. Okay, would you go into that business with that person? No. Okay, but I just don't know how things are cosmically. The same. The chances of it happening is still 0.6% or lower. So should you worry about that? No. Well, that's why I write to you. I said, yeah, but I'm spending half of my time responding to people who read these headlines. And the press are very irresponsible. Of course, there are very few journalists left. People are trying to scare us, right? Because that sells advertising. But they themselves said likely, and then 0.6%, right?
The 0.6.
Yeah.
Thank you.
And that's lower now. That was back then, whatever, 3 weeks ago. Now it's lower than that. The better we understand the orbit, the more we can predict how likely the possibility, and instead of going up, it's going down.
More questions?
Any online questions? Okay.
Okay, so we can close it here. Thank you very much.
Thank you. Thank you for the extra slide.